Hello, my name's Ian Evans. In this video we're going to be looking at three-phase transformers and the various connections. In previous studies you'll be aware of various aspects of transformers that come into play when things we need to understand when dealing with transformers. Basic principle of operation of a transformer is via the concept of mutual induction. So mutual induction from the various windings, basically the basic being the primary and secondary winding. Construction of a transformer, of course, takes into account the concepts of eddy currents and the use of laminated sections to reduce them to a minimum. And also the type of steel, so hysteresis being another iron loss, which is kept to a minimum through the selection of the correct grade of steel. Transformer ratios, we find that the primary voltage over the secondary voltage is proportional to the number of turns on the primary and the number of turns on the secondary, and inversely proportional to the current on the secondary and the current on the primary. We'll be using these when we look at the various connections later in this video. We need to be aware of our power formulas, of course. Here we have the single-phase power, the voltage times the current times the power factor. Where with three-phase power, we're dealing with the √3 times the line voltage times the line current times the power factor. The two basic configuration types we can see here are the star connection or the delta connection, and we'll see the how they're connected later in the video. Construction of transformers, of course, need to take into account the ability of cooling. Many cases you'll have oil-filled transformers, just based on convection, which can for both insulation and cooling. That can be increased, of course, by the use of pumps, radiators, and so forth. The percentage impedance of a transformer is important. You'll find that on the nameplate. It will indicate to us short circuit capacity. As you can see from the other formulas there, we have the full load current, which is determined by the kVA size of the transformer, and then the short circuit current, which is the full load current, then determined by the use of the percentage impedance. With the dot notation shown here, we use the dot notation to indicate instantaneous polarity of an AC winding, because we have AC, of course, is changing polarity. A 50 Hz supply every 10 milliseconds. We use the dot notation to indicate instantaneous polarity in relation to each other. When we use that in relation to the two basic connections, the first one here being the star connection, we use the dot notation to indicate that we have similar ends joined. Now there are various tests to determine the instantaneous polarity, so we can know for sure that when we're joining a star connection, we are joining similar ends, so that with the instantaneous polarity to provide us with a star connection. The second of the common connections is the delta connection. In this case, we join dissimilar ends of the windings. So, as shown here with the dot notation, we're joining dissimilar ends. We have to be careful to ensure that this is done correctly, and we have various tests that we'll look at through this video to determine that correct polarity. We're using an extra low voltage power supply here, a 41 volt 3-phase, 24 volt single phase, to supply our 2:1 ratio step down transformer. So this has a 41 volt 3-phase 24 volt primary, and it's a step down transformer. First test we're doing here is the resistance test of the windings. This is used for comparison purposes. What we can determine here with a step-down transformer, you'll find that the resistance of the primary will be higher than the secondary. Then we'll be looking, of course, for a balance on both sides on the primary for a balanced value, so that they're all equal, and the same on the secondary again, so that the three windings are balanced in terms of the resistance values. The first connection we're making here on the primary side is a delta connection. It's very important to ensure that you have correct polarity of a delta connection. So what we do here is we leave the last connection out, and we replace the last connection with a voltmeter. So as you can see here, we've replaced that last connection with a voltmeter. We've connected the supply and energized, and we're finding that the voltage across that last connection is around 2 volts for this particular transformer. That's indicating to us that although there is a little imbalance there and a couple of volts, it's indicating to us that we do have the correct polarity as shown on the drawing on the right, where we can see we have dissimilar ends connected with the use of the dot notation. So this can vary with the size of the transformers. I've had full voltage, 415 volt, 240 volt transformers where I've had about 20 volts, 20 volts on the last connection on a 415 volt primary, but that's still indicating to me that it's okay, because it's still a bit of an imbalance. To prove the point of an incorrect polarity, I purposely connected the primary here, the primary delta connection, with a reverse with one winding reverse polarity, as shown in on the drawing. We can see there, as before, we had 2 volts, a small imbalance. We've now got 86 volts, which clearly from a 41 volt supply, you can see is actually double the voltage. So you can see there's a clear distinction between a small imbalance and an actual reversed winding voltage, which is double the supply voltage. So there is no mistaking when you do have a reversed winding. Here we've reinstated our delta primary connection to the correct configuration with the as we see on the diagram to the right, with dissimilar ends joined. We tested that for the only got a small 2 volt variation, so we could safely after isolating the transformer, we could then safely make the last connection and then energize. On the secondary here, we're looking at a star connection. So as you can see, we've indicated on the drawing, we've connected on the secondary. We've connected the star connection with the similar ends joined. To do a voltage check to test our star secondary, here we're checking the phase each of the phase voltages. And as you can see from the reading on the meters, we're getting about 22 volts, which is a balanced reading on each of the phase voltages. We need to also check that the line voltages are equally balanced, as you can see from the readings here, 38 volts on each of the phase. Each of the line voltages. As with a delta connection, it's also important on a star connection that the correct polarity be checked. So again, in this case, we've purposely created one phase with the wrong polarity. So we have an incorrect polarity on a star on the star connection. Now, checking the voltages on that star connection, you can see here from the 3 line voltages that we have unequal voltages. So you see we have 22 volts, 38 volts, and 22 volts. You will find that if you check the phase voltages will be equal, but the line voltages, as shown here, are unequal. So this would cause grave problems, of course. If you try to run a motor or any other balanced load, and you would have a growling hot motor and so forth. So it's important that all the voltages are checked once you've done your connections. What we'll look at now is the various ways we can connect a step-down transformer. So we're going to see four different configurations of our 2-to-1 step-down transformer with the same input voltage, with 44 volt line voltage, and well, it's nominal 41 voltage but measured at 44, and 24 phase voltage measured at 25. In the first instance here, we have a star primary and a delta secondary. So we can see here from the the measured values. We've got the input to the primary. The line voltage is 44. The phase voltage is 25 volts. The line and phase voltages, which are the same in the secondary, because it's a delta connection, so there's only one voltage. So the line and the phase voltage are the same. We have 12.98 or 13 volts on the secondary. When we look at this same circuit of the star primary and the delta secondary, we look at it mathematically with ratios. We know that our ratio of the primary voltage over the secondary voltage is proportional to the number of turns on the primary and the number of turns on the secondary. Now, although we don't know the exact number of turns, we do know that it's a 2-to-1 ratio. So we can simply transplant that 2-to-1 ratio into the formula, because it doesn't matter how many windings there'd be on there. If there was 10,000 windings on the primary, there'd be 5,000 windings on the secondary. 20,000 on the primary, 10,000 on the secondary. It doesn't really matter, because it all comes down. It's all reduced down in the formula to a 2-to-1 ratio. So we can simply use the 2-to-1 ratio there. Now we have the we know the primary voltage. Now, when you look at a transformer, and we look at the formula we're using, it's all about the ratio of the voltage and the number of turns. Now, but it's all about the phase. It's all about the phase values. So we don't use line values. We don't go using the 44 volt line value input, because that's across 2 windings. And as I said, the ratios are all about one winding to another. So it's all about the phase values. So in this formula, we will use the phase value on the star primary side, which is 25.46. So as we move along in the formula, we can see that the secondary, when we transpose that formula, we end up with the secondary voltage secondary is 25.46 divided by 2. So our secondary voltage equals 12. It's calculated as 12.73. So it's fairly close to the to what we've actually measured. So with a few tolerances, of course. In this next configuration, we've changed the secondary from delta to star. So we now have a star-star configuration. So we have both line and phase voltages on both the primary and the secondary. Okay, so again we have the same input voltage, the 44 volts line voltage, the 25.35 phase voltage. Now, when we measure the phase voltage on the secondary, we've got 12.82 volts there. and then we've got 22.4 volts for the line voltage on the secondary. Now again, with that same star-star configuration, we'll then look at the use of the formulas, our ratios, and again we're utilizing the phase value when we're calculating the expected secondary voltage. We'll use the on the primary we'll use the phase value, because we must always work with phase values. So we've got 25.35 of the phase primary. We transpose that formula again to give us secondary voltage, which gives us 25.35 again divided by 2, which gives us a phase voltage of 12.67. Again, slightly different from the actual measured voltage, but again that's just tolerances. And when we went from the 12.67, if we want to work out our line voltage equals phase voltage times √3, which in this case gives us 21.94, which is pretty close to our actual measured voltage of 22.4. Now, the third configuration we're using is a delta to delta configuration, so a delta primary, delta secondary. Now, so we have our measured values here. So again, it's a 43.9 or 44 volts input, which is the line voltage. Now it's a delta input, so there's only the one voltage. So the line voltage is the phase voltage. So across each phase, we have 44 volts. So 2-to-1 ratio. You can see we've got measured 22.14 volts on the secondary. Now you'll notice that going back when we went back, we had a much lower voltage on the first configuration because we had a star primary. So there was a lower, the phase voltage was actually lower. Now that we've actually connected the delta on the primary, it means that we've got a higher voltage on the actual phase winding itself. So we've now got 44 volts across each phase winding, hence the higher secondary voltage. So again, we only have the one voltage on each side. So we only have as the line and the phase voltages are equal for a delta. So 44 volts stepping down to 22 volts. And again, looking at the use of the formulas, so again with our delta, we have we're using the ratios. We put the numbers in, but this time we're using the 43.9 volts because that is the actual phase voltage on the winding, and we transpose that. Gives us 43.9 divided by 2, which gives us 21.95. Again, which is pretty close to our calculated voltage given tolerances. Our measured voltage given tolerances. The last configuration we got here is the delta star configuration. So step down delta star, which is commonly used for distribution for step down transformers, 3.3 kV down to 415. You'll often see your high voltage 3-wire system to a delta primary, and then stepping down to a 4-wire configuration for distribution to either be domestic or commercial industrial supplies. So in this case here, our voltages are measured 43.8 for the line voltage, which is the same as the phase voltage, of course, for the delta primary. And then we have measured the 22.08 phase voltage on the secondary and 38.67 line voltage on the secondary step down of the winding. Again, using our ratios to calculate what we expect on the secondary from our primary input. We've got our again, we're using the 43.8 volts because that is the actual phase voltage, although it's also the line voltage because it's a delta connection. So it's the voltage that is across each of the primary windings. So a 2-to-1 step down gives us our 22.08. Or actually, the calculation here gives us 21.9 volts. Again, with tolerances. So the actual line voltage can be calculated from that. Which is line voltage equals the phase voltage times √3. So, like I said before, that's the most common configuration. So you can see from that the four different ways to actually connect the transformer, and the varying voltages that are available from those different connections. The final testing of transformers before energizing a course must be done in accordance with the verification section of the AS NZS 3000 2007, and also for portable transformers in accordance with AS NZS 3760. So I'm Ian Evans, and thank you for listening.